the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our conversation for precalculus on compositions of functions. And this time we're going to talk about applications of compositions, specifically just a couple, nothing really huge. And as is stated here in the text that I've written up, the strength of knowing how to work with compositions and what compositions are comes into play when we deal with real-world applications. Because our world is complex, even simple situations can be mathematically daunting. As such, learning how to simplify the complexity of these problems into bite-sized chunks will become a necessary skill. And by bite-sized chunks, I really am going to focus on tearing apart problems. You happen to know, or maybe you don't know, but the actual volume of a sphere. And so I should mention that sometimes people will say, oh, the volume of a sphere, or the surface area, sorry. The surface area of a sphere, which is going to be required for this problem, is the following. I'll call it S for surface area, is 4 pi times the radius squared. Now that, I really don't think that's very memorizable for any of my classes. My calculus students can derive that, but prior to that, I don't recall ever having that memorized. And to be very honest with you, I tend to forget it and rederive it if I need it. So anyhow, that is a straightforward, just kind of a gimme type of formula, just like, the area of a circle is pi r squared or something like that. We end up having this laundry list of formulas in mathematics, but that we can rely upon or look up. But what happens when we have the surface area of a balloon as it's being inflated being dependent upon how quickly the radius is increasing? So jumping into the actual problem, a spherical weather balloon is being inflated. The radius of the balloon is increasing at a rate of 2 centimeters per second. Express the surface area of the balloon as a function of time, t, in seconds. So we know the formula for surface area. We can look up, it's just that. But you can't actually look up this version of the surface area formula. So knowing how to deal with these types of problems is incredibly important. So let's see, the radius, we're told, is increasing at a rate of 2 centimeters per second. So not only is surface area a function of the radius, but radius is increasing with respect to time. And so we could say the radius is increasing at a rate of 2 centimeters per second. So the radius at any given time is just 2 times the number of seconds that have passed. At time 0, this is kind of important to note, at time 0, the radius of the balloon would be 0 because you haven't started inflating it. But at time 1 second, it would be 2 centimeters in radius because you're inflating it that quickly. I put the plus there because it's increasing, but there's no real reason to write that plus there, so I'm going to erase it. So notice we have two functions operating here. So now expressing this surface area of the balloon as a function of time instead of as a function of radius is not so terrible. All we need to do is substitute in the radius function in for r. That's all it really comes down to. So this happens quite frequently in science where you have a very complex problem and each part of the problem depends upon finer and finer detail.
Now, something I want to state here is that when I originally did this problem, I did not have that square on that power of 2t there. Surface area is a function of radius, but radius is a function of time. And therefore now surface area will be just a function of time. Now that mistake messed up this computation slightly, so when I zoom out in a second here, you're going to see that it's not 16 pi t squared, but it should be.
Now this nesting process which is really what composition is a bunch of nesting processes, can be made really interesting because you could say, like, for example, suppose that you have a function m that is equal to, I'm just going to make it very easy, and I'm going to say 8k plus 4. But you find out that k is a function that is equal to 3g plus 7. But you know that g is equal to 2f plus 4, and maybe f is equal to x plus 1. This is a nesting situation, and this is incredibly important when you get to calculus 1, because being able to break things apart into their component nests or composed functions is important, because you're going to do something called the chain rule in that course. So instead of writing k, and maybe I should color code this very quickly. There we go. So instead of writing k, I can write m as a function of g by substituting in 3g plus 7 wherever I see a k. So this k will be replaced by 3g plus 7. So plugging that in, I get 8 times k, and remember k is 3g plus 7. And then thing that I almost forgot was the plus 4 there. I actually had to re-record this little piece because I completely just ignored that. Distributing the 8 to the 3, you get 24g. And that g is blue. We have a plus 56 plus 4 more, so that's going to be plus 60. That number is going to get larger and larger as we move forward. Now, we are going to go ahead and replace g with 2f plus 4. So that g is going to be 2f plus 4. We'll go ahead and write that in. We have 24 times the quantity 2 times f, again, plus 4. And don't forget that we had that additional 60 at the end. And that does simplify down very, not very well, but it does clean up a little bit, right? 24 times 2, that'll be a 48f. And what do we have? 24 times 4 is 96, plus 60 is 156. Let me double check my mathematics there. 96 plus 60, yep, 156. That works out so far. Now, I see that I have this version of g here, but now I happen to know that f itself can be replaced just with x plus 1. And let me highlight that here. So that f can be replaced with x plus 1. This is actually the easiest of the group because it's a small multiplication. So let's go ahead and replace that f, 48, with an x plus 1. And we distribute through 48x. We'll have a plus 48 plus 156. This is, let's see, 48, 196, 204. And so this is our way of saying, yes, m originally was a function of k. It is true, but because k is a function of g, and because g is a function of f, and because f is a function of x, we could have written our original function, instead of as a function of k, as a function of x. And so rather than somebody saying, you know, m is a function of k, let's go ahead and work with that. And then somebody walks in and they say, oh, did you know that k is kind of varies in terms of g? In other words, if you change g, k is going to change. Oh, okay. So, and then somebody says, oh, but you know what? G changes in terms of f. So if somebody changes f, g will change. Oh, shoot. And then somebody says, well, but if f changes, it's because x is changing. So we've boiled it down to the first domino, I guess you could say, in that line that would change. And this boils it down to the very basic function that we could deal with. It is a a good skill to have to be able to work with nested functions and decompose or compose them, whichever way. So anyhow, that's how this style of example and application works. I did say there are a couple examples here, so let me hop forward. One final example. It's nice to see how compositions can help us derive famous formulas using something called iterations. Suppose your savings account earns 5% interest compounded annually. If you invest X dollars in such an account, then the amount, A of X, of the investment after 1 year is the initial investment plus 5%. So again, you have a 5% interest bearing account. After one single year, if you had invested X dollars into it, and let's just say it's simple compounding interest, so you just get 5% a year. So you have your original amount and you have 5% of that original amount that you add to it. Obviously, that is going to be 1x plus 0.05x, which is 1.05x. Great. And then I ask you to find and interpret the composition A with A. And then interpret the composition A composed with A composed with A, and so on and so forth. Now remember, A itself is just the amount of money we have after 1 year if we have a 5% interest on an investment. A composed with A, well, that takes A, which we've said is 1.05 times X, but instead of X, we're plugging in A. That's all. Well, we happen to know that A is 1.05 times X. Okay, so again, it's just because A itself is 1.05x. And you could multiply out, grab a calculator, multiply those out, but it's actually nicer for this problem to leave this as 1.05 squared times x. Now we move on and we say, okay, well, what if we had A composed with A composed with A of x? Now, if you do this, you get 1.05. Actually, I'm just going to do it this way. We have 1.05 squared. I'm just using A composed with A. And we're going to compose that with A. So this is A of A. And instead of plugging in X, I'm going to plug in A to that. And of course, A, again, is this guy up here. So this is going to be 1.05 squared times 1.05x. And if you multiply those two together, you get 1.05 cubed times x. Now to interpret what these mean. Well, let's pretend as though you had $100 that you invested. This is just the easier way to interpret this. If you invest $100 at 5%, everybody knows that if you get 5% back, or on top of that, you have 105. So that's what this mathematics does for us here. It brings back $105. So at the end of that year, we have $105. Now, before I plug this into the next composition, A composed with A, I just want to ask, what would you have if you let it ride for 2 years? So in other words, the first year, at the end of it, you now have 105, and you just say, rather than pulling that money out, I'll wait another year. Well, if you wait another year, you would have that original $105. When I say original, I mean the $105 after the first year. And then you'll tack on 5% of that $105, right? And if you do that, notice you have one of these $105 and another 5% of those $105. Or in other words, you have 1.05 times that $105. But remember, that $105 that you originally had was the product of 1.05 and 100. And so really the amount you should have after that second year is this, which, by the way, if you didn't know, that's $110.25. But if you see the pattern, so after 2 years, or you should say after 1 year, you have 1.05 to the first times $100. After 2 years, you have 1.05 squared times $100. After 3 years, you'll have 1.05 cubed times your $100 or whatever your initial investment was. So find and interpret these compositions. Well, A composed with A composed with A composed with A, the very last one, is 1.05 to the fourth times X. And this is, each of them is basically the amount you have after that many years. So this is the amount we have after 4 years. And if you did, let's just pretend, dot this down. Let's suppose that you had a composition that did this. And this composition went, let's pretend, n times. So you compose A with itself n times. Well, just looking at the pattern here, that 2 compositions gives me a square, 3 compositions gives me a cube, 4 compositions gives me a 4, then n compositions should give me 1.05 to the nth power times x. And again, that should be the amount that we have in that account after n years. And so this is a really good use of compositions. It's a really nice style of problem. Very gentle kind of working with compositions here. Really nice style. But it's good to see that compositions can be incredibly important. And as I said, since you're in a pre-calculus course and you're going to be moving into calculus, you want to know that these compositions that you learn early in your algebra career, that they end up becoming useful. Because what I really think most students dislike is to learn something that they never are supposed to use ever again. And I think that's silly to do that, honestly. There are some concepts in mathematics that are worth learning even though you don't use them in the future. They're good critical thinking kind of exercises. However, it is important, in my opinion, to spend a lot of time on concepts you will be using. And compositions, that's a concept you will be using.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.